Hello everyone, welcome back. And the topic of this lecture is sign of radial velocity. Consider you have transmitted a signal from the CW radar having a frequency f0. If the target is stationary, then it will return the same frequency f0. No Doppler shift, no relative motion in the target. If the target is approaching you, then the shift will be in positive direction. That is, approaching target gives you a positive shift. If the target is going away from you, that is called as receding target. If the target is receding, then the Doppler shift will be negative and it is f0 minus ft. Measurement of Doppler direction by a two-phase synchronous motor. Now, how can we say that whether the target is approaching or receding by seeing FD? For that, the arrangement which is shown in this figure is very beautiful. See here, the CW transmitter, continuous wave transmitter, transmit a continuous sine wave into the atmosphere using this antenna. Now the output of this antenna is f0. A part of this f0 signal called leakage signal will be supplied to two mixers, mixer A and mixer B. Mixer A is supplied with direct signal f0. Mixer B gets a signal which is phase shifted. This phase shifting concept we have seen in single side modulation of analog communication subject. So this is 90 degrees phase shifted signal supplied to the mixer. These two mixers get one signal, like here for mixer A it is f0 directly, and mixer B it is 90 degrees phase shifted f0. The other signal to this mixer and this mixer is f0 plus or minus fd. CW radar signals echo will have a frequency shift depending upon the movement of the target. Now the signal which is coming in this antenna is either f0 plus fd or f0 minus fd. Now this channel A and channel B will process the signal and if one channel A is positive, channel B will be having negative magnitude. Because of this synchronous motor rotates in one direction. Let us say if it is rotating in the clockwise direction, we can estimate that the target is approaching us. If it started rotating in the opposite direction, we can understand that it is receding target. Now any signal which is transmitted, let the transmitted signal is given by Et is equal to E naught cos omega naught t. This is standard representation of any sine wave, a continuous wave. The echo signal from a moving target, that is return signal. The incident signal is having three changes related to the echo signal. There is the same signal goes, hits the target and comes back in the form of ER. These two signals have three kinds of difference. One is the incident signal strength is E naught. Definitely the echo signal will be very weak compared to this signal, so we should multiply this E naught with a constant K. So K1 E naught. The incident energy frequency is f0 with 0 phase, plus 0 here, plus 0 phase. Whereas the received signal will have a shift of WD, omega d, depending upon the direction of the target. Omega naught plus Fd for approaching target, omega naught minus Fd for receding target, plus this is phase change. 1, 2, 3 differences between these two signals. Now the output of channel A is given by channel A is getting one input is E naught cos omega naught t. Second input is K1 E naught cos omega naught plus or minus omega d plus phi. That omega naught of one input and the other input gets cancelled. It is left with K2 E naught plus or minus. See here, these are the two signals that are given to the mixer. So this omega naught gets cancelled, only this will left, that is shown here, omega naught d plus phi. Similarly, the other channel will also get a signal of same kind, but a phase difference of plus 90 degrees will also be there in channel B, channel A and channel B. These two signals are given to a synchronous motor. That means these two signals are going to be added up. If the target is approaching, the outputs of from the two channels are this. Both are in having positive phase changes. The difference between these two signals is this signal is 90 degrees away from this signal. That means if this is cos 0 is 1, this will be cos 90, which is 0. So one is 0, another one is at one terminal it is 1, another terminal it is 0. If it is cos 90, this will be cos minus 180. Like that, the motor direction will be in one particular, motor will be rotating in one particular direction. When it has changed the direction, when the target has changed the direction, the motor, the same similar equation with minus signs represents the change of reversal of motor direction. So by seeing the motor direction, you can estimate whether the target is approaching or receding. In the next topic, I hope you understood this. In the next topic, we are discussing the applications of CW radar. CW radar main application is measuring the velocity of target. The inability of CW radar is it cannot measure the range, that is distance between the target and the radar station. That it cannot do. What it can do? It can measure the velocity of the target very accurately. Calm down. Let us read this point. CW radar is used to measure the measurement of the relative velocity of a moving target. Rate of climb meter for the vertical takeoff aircraft. Consider a rocket which is taking off. The distance how much distance it has traveled is known by the CW radar fitted to that rocket. That is rate of climb meter for a vertical takeoff aircraft. CW radar has been suggested for the control of traffic lights, regulation of toll booths, vehicle counting. As discussed in the previous videos, radar is best suited for the count of vehicles and control of vehicles. So CW radar can control traffic lights, regulation of toll booths, vehicle counting. All this can be done using the CW radar. For in railways, CW radar can be used as speedometer. It is used for the measurement of the velocity of missiles and baseballs. Just now we have talked about rocket's velocity. climb rate. Now this is measurement of velocity of missiles, baseballs. It is used for the measurement of turbine blade vibration. If a turbine is rotating and its blades are vibrating at that velocity, at a very high RPM, the turbine blades are rotating. There, manually we cannot measure the vibration. Using radar, we can do that very easily. Measurement of speed of grinding wheels, because it will be moving fast. We can measure at what rate the grinding wheel is moving. That we can do very easily, comfortably. Monitoring of vibrations of cables and suspension bridges. See, this CW radar is very accurate that it can tell you the velocity like 80.46 kilometers per hour. So that much accurate is this CW radar. So using this radar, if you are standing under a bridge, because you might have experienced always the bridges are vibrating, a cushion will be given. If you are standing under the bridge and started using this CW radar to measure the vibration, you will definitely get at what rate, how much vibration that the bridge is getting. A high-powered CW radars for detection of aircrafts and other targets. Why it is high-powered CW radar? Because CW radar don't have the limitation of maximum and ambiguous range, or range limits are not there for the CW radar. So CW radar, if its range, if its capacity is not enough, increase its power, its electromagnetic signal can go to a far distance and come back with information. So increase the power, have large range. That is why it is called as high power CW radar for detecting aircrafts and other targets, because aircrafts will always be very far away from the base station. So you need to have high power CW radars, which are also called as ground based CW radars. Okay, I hope you understood all these interesting applications of CW radar, and you understood the previous topic also. Thank you for watching. Bye bye.